Alright, if we've covered the law of gravitation, basically what that said was we got two masses here, M1, M2, and if you look at their separation, that separation is R. From their center of masses, you can calculate the force of gravity, which is Fg equals G M1 M2 over R squared, where we said again that G is 6.67 times 10 to the negative 11 newtons times meters squared per kilogram squared. Alright, so it has numbers and units. And this gives us the attractive force between any two objects. And we said that, for small objects it's really insignificant, but when you have planetary bodies, then you really start to see the force of attraction in play here. So we're going to go through a few derivations, if you will, of expressions involving the second law and the force of gravity. So if you want to think about, let's say, the planet Earth here, and you got some person in free fall here, and you wanted to look at their acceleration due to gravity. Basically, this person, we're going to say that their mass is little m. We're going to say that the big mass, in this case Earth, is big M. And then what you have to realize is that they are separated not by this tiny distance here, but by this distance, the radius of the Earth. So what you can do is you can take a look at the forces and the second law, and let's take a look at what ends up happening here. So this person's accelerating down, and I would say that, well, okay, if they're accelerating down, sigma F equals their mass times their acceleration. And the force acting on them is the force of gravity. That's it. That's what our free body diagram would look like. So let's write F of G as sigma F. But now what we can do is we can write F of G as big G, mass of the person, mass of the planet, over the radius of the planet squared. And what you're going to find really quickly is that it doesn't matter what this person's mass is, that doesn't determine their acceleration. These quantities, however, will. So the acceleration due to gravity that this person is going to experience is going to be equal to Gm over R squared. Now, if you put in the values for Earth, mass of the Earth is 5.97 times 10 to the 24 kilograms. And radius of the Earth is 6.37 times 10 to the 6 meters. You put those values in and you put in G, what you're going to get is approximately 9.81 meters per second squared. That's where that comes from. So we have the ability to determine the acceleration due to gravity G at the surface. All you have to do is put in these numbers here. Big G, mass of the planet, over radius of the planet, and you square it. And this gives you the acceleration at the surface. Now, one thing I want you to be aware of is that this would work anywhere, not just the surface. So if you happen to say, okay, well, what if we put some person up way out there? A lot of people go, isn't it zero gravity out there? And there's absolutely no way. There's a force of gravity acting on you. And this thing would actually pull you towards the Earth, and you would end up colliding with the Earth at some point. And you're a different distance then. All right, so let's just call that R. And we'll call it lowercase r, because it's not the radius of the planet anymore. It's a lot farther out. Let's just, for the sake of argument, say that this is equivalent to 2re, but we'll use the lowercase r. In general, the expression would just be g little m over r squared. It's the same thing, it's just we're not dealing with the radius of the planet anymore. That would give you a different acceleration due to gravity. So one thing we can do is we can calculate, well, what would their acceleration be out there? It would obviously be something different because you're dealing with a different value of r. So if we did a value of 2r, what we would get is actually a quarter of the value that we would get here, because what we're doing is we're doubling r and we're squaring it. So if I do the calculation of G, mass of the planet, and then this distance, which I'll say is twice the radius of the Earth, twice this number here, I'm going to say that this person ends up accelerating at 2.45 meters per second squared. So you get something significantly less out there, but it's definitely not zero. So these expressions here will give us the surface acceleration due to gravity, or they'll give us the acceleration due to gravity anywhere we want around the planetary body.